Hello and welcome to the AutoPIPE Vessel webinar. My name is Sudeep Ganguly. I'm a Senior Technical Support Engineer with Bentley Systems in California supporting AutoPIPE Vessel. Today's webinar topic is cost savings using design optimization and new advanced loadings. Today's seminar would begin with a brief introduction to the AutoPIPE Vessel software, followed by an overview of the graphical user interface and the cost estimation module of the software. The webinar would cover mainly discussion on design optimization and cost reduction based on several case studies. And finally, there would be presentation on the new advanced motion and blast loading features that would be available in the SS1 release in September. AutoPIPE Vessel powered by Microprotol is a very powerful software that can design virtually any type of pressure vessel, air cooler, heat exchanger, and storage tanks to most of the major global design codes like ASME, European, and British. One of the strengths is the ability to import thermal design data from HTRI, Aspen, ProSim, and Honeywell, as well as exporting to the major CAD software and plant design software like PDS and AutoCAD SolidWorks MicroStation. The software is ideal for both EPC companies as well as equipment design and fabrication companies. There are several advantages of the software, including maximizing productivity of skilled engineering resources, supporting a global market, and improved collaboration across distributed project teams. AutoPIPE Vessel offers a wide range of global vessel codes, including regional wind and seismic, including last 10 years of all design codes from French, American, British, German, Russian, and European. It also supports local load analysis methods and comprehensive regional seismic and wind loadings for Canada, India, ASCE, European, Russian GOST, British, Brazilian, and Spanish. There are several users worldwide, including major EPCs using AutoPIPE Vessel like Jacobs, Technip, and Saipem, nuclear EPCs like Areva and Babcock & Wilcox, inspection authorities like Lloyds, SGS, and Bureau Veritas, as well as oil and gas companies like Petrobras and ExxonMobil. Shown here are examples of some of the equipment designed using AutoPIPE Vessel. From top left, a reactor vessel with many nozzles in close proximity, a distillation column with platforms and stairs, air cooler with all structural elements, a vertical jacketed vessel on skirt. Almost every TEMA type shell and tube heat exchanger mechanical design can be performed, including some examples shown here, like a stacked heat exchanger, multipass exchanger, kettle type reboiler, and U-tube exchanger. AutoPIPE Vessel has powerful CAD export feature, generating 2D drawings and 3D models for MicroStation, AutoCAD, and SolidWorks. Shown here are some examples of 3D SolidWorks model created automatically from a designed exchanger using the interface feature. Let's watch a quick demo of AutoPIPE Vessel GUI and the cost estimation module. The GUI in AutoPIPE Vessel is divided into 4 sections: the item numbers on the left, the 2D view on the top right, the 3D view at the bottom right, and the analysis section on the bottom left. The vessel properties can be entered in one dialog box. This includes all the codes for the design. Wind, motion, earthquake, and blast loadings are entered in the respective tabs. Design conditions are entered in the design conditions tab. Now this is how the equipment looks before design. After design, the color is changed. The optimum design is shown with all the detailed dimensions like reinforcement pads for nozzles, etc. are shown. Final design dimensions are shown in the GUI, in the geometry section, including nozzle details. Now let's look at the cost estimation module. The cost estimation is performed from the model data, the design model that was created. The bill of material is already created automatically. One can look at the individual components to check and review the data. The most current market rate for materials can be entered in the materials window. And finally, the Excel sheet for the cost estimation is generated. This shows the details of each and every component. The raw weight, freight weights are calculated, rates are applied to arrive at the total raw weight cost. Cutting, preparing, rolling, assembly, welding, all these hours for individual components are calculated. And finally, this shows a summary. This is the complete details of all the cutting, preparing, assembly, welding rates. This is the total manufacturing cost, the engineering, subcontracting, inspection hours. The material costs are listed here after calculation. And finally, the grand total of the manufacturing cost is calculated. User can also input margin and sale price, and the final estimated cost is arrived at, which is $139,930. The customization of the cost estimation model can also be done. Rates and time can be entered conveniently. So why do we need to optimize the design of pressure vessels after all? In a typical petrochemical complex or a chemical plant, there could be more than 100 pressure vessels of various kinds. The static equipment, which includes pressure vessels, heat exchangers, storage tanks, air coolers, etc., constitute a major portion of the plant's initial capital investment. Particularly equipment subjected to extreme service conditions, including very high temperature, pressure, corrosion, and erosion, like chemical reactors, for example, fluidized bed reactors, which are primarily made of high nickel alloys like Hastelloy, Incolloy, and other heat-resistant alloys, may cost several $1 million a unit because the material construction is very expensive. In fact, they are typically one of the most expensive single piece of equipment commissioned in any plant. Hence, besides safety and durability of the equipment, cost reduction of static equipment, including pressure vessels, is very critical. Over-designed equipment or equipment not optimally designed translates directly to increased capex and longer break-even period for investors. Optimization is also essential for utilization of material in stock or short delivery requirements. The Vessel Properties dialog box in AutoPIPE Vessel has the Design and D-Check options. The Design option, which is set as default, is one where the software performs the complete design and optimizes every pressure-retaining component based on basic user inputs like length, diameter, and design conditions for the equipment. At the end of the calculations, the software alerts the user with errors and warnings for necessary action. The D-Check option is used to check an existing design in which the software does not optimize the design but performs only code checks and calculations to ensure the design meets code requirements and alerts the user regarding any deficiency with error messages and warnings. Let's take a quick look at the optimization logic of the software. First, the internal and external pressure cases hydrotest pressure calculations are performed and thicknesses determined, followed by vibration period determination and calculations for wind load conditions. If there is overstress, component thickness is increased, else it proceeds to calculate for a seismic load case. If the equipment is a vertical column and there is a specified maximum column deflection to be maintained, the software checks for that, and if that condition is satisfied, it proceeds to seismic load case calculations. If the seismic calculation fails, the thicknesses are revised, else it proceeds towards nozzle reinforcement check and performs necessary optimization action for nozzle design. Finally, the calculations for base, anchor, saddle, etc. are performed and the report generated with the load case calculations. In this section, we would get into more details of the nozzle design optimization and associated cost reduction. Shown here is the dialog box for the nozzle design. The nozzle size can be defined in terms of nominal pipe size, DN, internal or external diameter. Options to input reinforcement size and most reinforcement types, including long weld neck, self-reinforced, butt welded, are available. For a conservative design, the user may limit length of nozzle or shell or exclude areas on the pad, nozzle, weld, or shell in the design calculations. Location, orientation, offset, and inclinations are entered in the locations field. Set in, set on type with specified nozzle projections and gooseneck type nozzle can be designed as well. The nozzle loads can be entered manually or automatically imported from AutoPIPE analysis file. Fill from standard button allows importing sustained nozzle load from the standard template in the library. The nozzle loads can also be submitted for FE analysis in Nozzle Pro. We would now review a couple of case studies related to design optimization and cost reduction. In the first case study, we would consider the nozzle design optimization for the nozzle N1 shown above. Here, a design was performed for a carbon steel vessel, shell OD being equal to 1400 mm. The first design condition is 200 degrees centigrade temperature and 0.5 megapascal pressure. The nozzle reinforcement type is set at the default repad option. The calculated shell thickness is 6 mm. As you see, the software automatically calculates the nozzle N1 dimension details, including that of the nozzle reinforcement pad, and also the rating is automatically determined as class 150. Observe that the thickness of the pad is maintained same as the shell thickness at 6 mm. Same model is revised by 2 successive iterations with design conditions changed to 230 degrees C temperature and 1.5 megapascal pressure, and subsequently to 300 C temperature and 5 megapascal pressure, which leads to increased shell and nozzle pad thicknesses. Also, the ratings are calculated to be class 300 and 600 respectively. When the pressure is further increased to 15 megapascal, notice that the reinforcement pad type nozzle is automatically changed to self-reinforced type, and the rating increased to class 1500. This is because for the design conditions of much higher pressure, the reinforcement pad option is no longer viable, and the software's optimization engine assigned a self-reinforced type nozzle, although the initial selection was with reinforcement pad. The second case study discusses how in design phase, common assumptions by the designer may lead to higher final cost of equipment and how this can be easily avoided using AutoPIPE Vessel. Shown here is the previous example with 2 more nozzles added, N2 and N4. While deciding to select between nozzle with reinforcement pad and self-reinforced nozzles, the nozzle with reinforcement pad was specified since self-reinforced nozzle usually cost considerably more than regular nozzle. The understanding was that this would keep the overall cost of the equipment low due to lower cost of component. The total estimated cost was approximately $36,000. The same equipment now with self-reinforced nozzle, interestingly, was found to cost significantly lower than the option with reinforcement pad type nozzle, which is counterintuitive since self-reinforced nozzles cost more. The reason for more than 11% cost reduction was the elimination of cost of pad materials, welding, machining, and all the associated labor costs in this particular case, which are incurred in the reinforcement pad type option. Therefore, the actual estimated cost can sometimes be counterintuitive, and it is not possible to decide between various design options unless the estimated costs of all possible cases are individually analyzed. This would lead to better decision making and reduce total cost. Another case study is presented here which talks about the effects of having a stiffener for external pressure design on the vessel cost. The example from case study 1 is considered. In order to eliminate the need of the stiffener, first the model is made without stiffener by unchecking the option in the Vessel Properties tab, as shown on the left. In the Component Properties dialog box for the transition cone, the knuckle radii for the large and small end of the cone are specified. The cone plate thickness is computed equal to 15 mm and the total cost is estimated at $22,000. To compute the cost of the equipment with stiffener rings, the option is enabled as shown on the left, and the knuckle radii are removed and the analysis is run. As we can see in this case, the cone thickness is significantly less and is the same as the shell thickness for the whole vessel at 6 mm. The cost is likewise reduced by 12% to $19,425. The cost reduction is 50% due to material reduction and 50% due to labor, machining, and welding cost reduction. Material cost calculation is simpler, but calculation of accurate labor, welding, machining costs is much more complicated, which AutoPIPE Vessel performs to a high degree of accuracy. The cost of material can have significant impact and can further increase the difference in cost for various design options. As seen in this fourth case study, the same equipment from the previous example, but using stainless steel now is used and is evaluated for the external pressure options, with or without stiffener rings. The cost is significantly reduced by 29% using stiffener, and this difference is much higher than the carbon steel case. Let's talk about optimization of body flange design. Body flanges can be a very expensive component of a pressure vessel, particularly if the material of construction is expensive, for instance, nickel alloys or stainless steel. Hence, performing an optimum flange design is critical for a cost-effective solution. AutoPIPE Vessel Body Flange Design Module offers several optimization methods, for example, EN13445 Annex to G with compression rings, loose and bolt tensioning options. There are 4 options available for optimization based on hub stress and gasket circle reaction optimizations, and also another design method based on bolt load, namely design, full or controlled bolt load. Shown above are the results from a case study on the design of a body flange using the hub stress and gasket circle reaction based 4 optimization methods available in AutoPIPE Vessel. In summary, one can easily observe how much difference in cost each of the methods can result to. Options 2 and 4, which are the higher cost options, lead to a much more safe and conservative design with significantly reduced hub stress, but with 40 to 55% cost increase. Options 1 and 3 result in more compact flanges with smaller hub length and flange diameter, but at the cost of higher hub stress. Hence, the optimization method provides a valuable iterative approach to arrive at the most optimum design based on the cost versus performance criteria. Our last case study for today relates to a vertical distillation column with trays. AutoPIPE Vessel has the option to specify the maximum deflection of tray in the wind tab, as shown to the left. This is mainly to prevent spilling of liquid from the tray when the column deflects. In this particular case, maximum deflection would assume default value since no value is specified by the user. The program calculates based on the allowable deflection, and the obtained deflection is well below the allowable, with 6 mm computed vessel wall thickness. In this case, the same column is modeled, setting a more stringent 2 mm maximum deflection in the wind tab. The program considers 2 mm maximum allowable deflection, and the maximum deflection of 1.98 mm is maintained just within the allowable limit. Observe that due to the severe restriction in allowable deflection, the wall thickness is significantly increased. But also observe how the program optimizes the thickness along the vertical section with thicker walls at the bottom, where the bending moment is larger, and thinner sections for the top with decreasing bending moment. Our last section for today's webinar is about the two new advanced modules that would be introduced in the upcoming SS1 release of the software in September this year. The first of which is the motion analysis module. The main motivation for development of motion module was to enable users to determine stresses and moments arising in vessels transported on barge, ships, or even during ground or rail transportation. Once a vessel is fabricated, it is handed over to freight forwarders and logistics companies who, although are expert in their own fields, do not have knowledge of pressure vessel design or structural analysis, and fail to determine exactly how much stress the equipment can experience due to the inertial forces during transportation. As would be seen in one of the slides, the stresses and moments due to motion can be quite significant. It is also used for analysis of floating production storage and offloading FPSO, as well as analysis of floating liquefied natural gas FLNG equipment. Let's watch a small video demonstrating the forces exerted on a cargo during sea transportation. So this is exactly an example of a pressure vessel transported on a ship. Now it shows one of the lashings are already broken. Now the vessel is already overboard. The forces generated during transportation due to the wave motion is so intense that it actually broke the lashings of the pressure vessel and it went overboard. The new motion module in AutoPIPE Vessel can be used for both horizontal as well as vertical pressure vessel. For horizontal vessel, the motion module enables input of acceleration in two horizontal, that is axial X and transverse Z, and vertical Y directions, and there are total 6 combinations. The forces can be applied both for operating and shutdown conditions. For vertical vessel, the module enables input of acceleration in the transverse and vertical directions, and just like horizontal pressure vessels, the forces can be applied in both operating and shutdown conditions. The motion analysis can be combined with wind analysis under the motion tab in GUI. Multiple level step input for normal and abnormal load conditions are possible. This is how the report looks. The vertical, axial, and transverse accelerations are plotted as 3 different curves as shown. The report also shows the accelerations for the normal condition and for the exceptional condition. A comparative analysis to show the effect of transportation forces is shown in this slide. First, an analysis was done by using only wind dynamic pressure of 100 decanewtons per square meter and without considering wave motion. In the second analysis, the motion analysis was done with a 5.5 meters per square second and 3 meters per square second acceleration in the 2 horizontal directions and 3 meters per square second in the vertical direction. Also, a wind dynamic pressure of 100 decanewtons per square meter was applied. Observe the difference in the bending moments and maximum deflections for the 2 cases with and without motion. The differences are quite significant with even a reasonable acceleration. When the motion inertial accelerations are included, the bending moment and maximum deflections increase by more than 300%, which would apply significantly more stress on the vessel wall, something that needs to be factored in to prevent damage during the shipping. These are screenshots from the report for the analysis with and without motion case. Similar to wave motion, blast loading analysis is also a new addition. The reason for considering blast loading while designing a pressure vessel are multitude. In recent times, there is increased threat of terrorist attacks. Also, an accident in a plant can lead to explosion with catastrophic consequences and severe damage to the vessel. To prevent loss of life and severe damage due to a chemical release, containment of vessel contents is very important in the event of an explosion. An effective mitigation of damage to vessels during blast would be to look into the structural resistance and physical integrity of the equipment during such an incident. There are two forces that are in effect during a blast. There is a shock wave which propagates and passes over the vessel. This is treated as a dynamic wind pressure orders of magnitude higher than what would be typically used to design for a wind loading case. There is also static overpressure which is applied as a compressive force on the exterior of the structure. The first schematic shows the propagation of the shock wave. The refractive wave of explosion near the ground combines with the planar wave, hence augmenting the total shock effect. The second figure shows the variation of the blast pressure and shock velocity. They diminish with the distance from the source of the explosion. Here is the GUI for the blast analysis. As mentioned earlier, the dynamic pressure and overpressure are entered in the relevant fields. There is a provision for mentioning vessel shape factor as an option. The Materials tab has been modified to accommodate addition of exceptional allowable stress for the blast load analysis case. The exceptional allowable stress field enables user to input a much higher value of allowable stress than the regular design allowable stress only for the blast loading case. This would allow the stress to go over the design allowable stress but be contained within failure limit, hence preventing catastrophic failure of the equipment. Separate calculations are performed for the blast loading conditions. Component calculations are performed for blast overpressure. Calculations are done as external pressure. The screenshot shows the list of components for which the external pressure calculations were performed for the blast load analysis. Also shown a typical external pressure calculation for a specific component. So this brings us to the end of our webinar today. I'd like to thank everyone for attending this webinar, and I'd like to invite you to join us for additional webinars that will be occurring in the coming months. Thank you.